Our next speaker is Brandon Shapiro of the University of Virginia. His title is Finite Posets as Algebraic Expressions in Duoidal Categories. Over to you, Brandon.
All right, thanks so much. Really appreciate you having me, and that this conference has continued on. It's always been one of my favorites. And yeah, so everything I'm going to talk about here is joint with David Spivak, and the bulk of this was done when I was at the Topos Institute with David, but now I'm at University of Virginia. So first things first, I should tell you what duoidal categories are. So first of all, we have two monoidal structures on our category, where I and J are meant to be the units, and tensor and this triangle operator, which I'll call tri, are meant to be the two tensor products. And there's a couple different ways to define it. So the most sort of concise is saying that the second monoidal structure, tri and J, when we regard them as functors, are lax monoidal with respect to the other one. So if we use I and tensor on both copies of C here and on C here, we get that J and tri are lax monoidal with respect to that. If you unwind that definition, then you get that it amounts to basically these four natural maps. Well, three morphisms down here between the two units and their products, and this interchange morphism that says that a tensor of tris is not equal to, but has a morphism to the tri of tensors. And in a minute, I'll give what I think is a really illustrative example of that. And then we have various associativity properties of these, for instance, that demand that these maps make J a tensor monoid and I a tricomonoid. But we won't need that so much today because I'm going to be interested in what we call physical duoidal categories. And the motivation for this name comes from an example I won't really get into today, but the idea is to think of tensor as putting two things next to each other in space, and tri putting things next to each other in time, where there's a causal dependency between them that's not there in the space case. So sort of going from that intuition, we demand that the tensor is symmetric. In fact, it's often going to act like a disjoint union, and that symmetry is compatible with our other structure, and that the two units I and J agree. And so all of these three morphisms are then going to be isomorphisms. And so we can treat it like there's really just one unit. And our original motivation for physical duoidal categories came from the theory of polynomial functors, which I'm not going to talk about today, but features heavily in the paper that I reference at the end. Instead, I'm going to talk about what my favorite intuitive example, which we'll ultimately find is very fundamental to this structure. So, namely that of posets. So I'm going to keep at the top of the slide sort of a summary of the previous slide. So what it means to be a physical duoidal category. We've got this interchange morphism, symmetry of the tensor, and agreement between the units. So for posets, the unit is going to be the empty poset. And that's going to be a unit for both of the monoidal structures, which on elements are both going to look like the disjoint union. So in particular, tensor is going to be just the actual disjoint union of posets. And tri is going to be what I call the join of posets. Not 100% sure how standard that terminology is, but it's consistent with other uses of the word join. And what it means is you take the disjoint union of two posets, and then in addition to the relations you already have, you add in a relation from every element of the first one, P, to every element of the second one, Q. So this arrow here should really be like a big like crisscross of arrows going up for every combination of objects in P and Q. And I'm generally going to use these sort of arrow diagrams to talk about posets, where these arrows will sometimes represent more than one arrow, like here. So the interchange morphism has this really nice form in posets, where on the left side, this tensor of tries is what we have for posets, disjoint union them all, and add in all the morphisms from P to Q and from R to S. And then on the right side, we disjoint union P and R and Q and S first, so that when we take the join of those two, we also have these cross terms. The elements in P are related to those in Q and in S, and same with those in R. And so this is kind of similar to like if we were taking like tensor to be plus and try to be times, you get these cross terms when you multiply two sums. And that's related to the example in polynomial functors to some extent. But yeah, so this is I really like this example because it really shows like why we often want something like this. And additionally, it is going to be sort of a universal example in the sense I'm about to describe. There's a question, if I is iso to J, is there some sort of Ekman-Hilton argument in action relating tensor and trie? Right, so if this interchange isomorphism if this interchange map were an isomorphism, then there would be an Ekman-Hilton argument showing that tensor and trie are isomorphic themselves. But because it's not an isomorphism, you don't get that. So then it would be a braided monoidal category. Well, rather, let me clarify. So a duoidal category with that property would be braided monoidal. In this case, we're assuming tensor is symmetric. So
can I jump in? But you do get a map from tensor to trie, right?
Yes, and I will.
Okay.
There's a few. There are some different ways to see that. One of which will be on the next slide. So very glad you asked. Yeah, so ultimately what I'm going to do next is sort of talk about how we figure out what are all these maps that we get, because in a physical duoidal category where we have the symmetry and these units agree, as you suggest, we get a lot more maps that we don't have in a general duoidal category. You don't necessarily have a map from tensor to trie in a duoidal category, but with this additional assumption on the units, we do. And so how do we see that, or maybe answer questions like that more generally? So yeah, so what are the different kinds of operations and maps between them that we have in this structure? So we could take arbitrary combinations of tensors and tries. So this map here comes from plugging in the identity for B in the interchange map, still written at the top. If you also plugged in the identity for C, then you would get A tensor D mapping to A trie D. But in this case, we have a really nice visual way of seeing how these work, because we can actually use the example of posets and treat these variables A, B, C, D as singleton posets. So you can build a poset like this from the expression on the left, where we start with, if you're going from inside the parentheses, you start with C join D, so that's the two-element poset with a relation. You tensor it with B, so that's the disjoint union of those two. And then you join A with that, which puts the A at the bottom and a relation to everything else. And you can build a lot of posets this way, and I'll get more into which ones later on. But the really cool thing is that this also tells us what the maps should be. So if we do this for the next two expressions, we see that these are slightly simpler posets, but the map between them here coming from the duoidal structure, just like for the interchanger, we saw it was sort of the inclusion of two single arrow posets into the cross terms. We can see that we have other maps like this as well that come from the fact that we have these shared units, but we can see just in terms of the posets. And in fact, this is going to be a complete heuristic for when we have a map. So for instance, going from a tensor B to a tri B is just going from, A and B placed disjoint to each other, the discrete two-element poset mapping into the two-element poset with a relation from A to B. So we can see all of this more geometrically. And in fact, we proved that all of the structure maps between two expressions in a physical duoidal category are the same as the monotone functions between their corresponding posets, which are bijective on the elements of those posets. And that comes from the symmetry of the tensor product, why we use bijections instead of identity on elements. Yeah. And so what for me, this was really motivating, because we were working on trying to understand these operations we had on polynomial functors better, and what we found was this structure very close to duoidal categories, and describing some of the duoidal categories we were seeing, we could work out entirely what these maps were just by taking expressions, drawing their posets, and deciding just by looking at it whether or not there's an inclusion there. And especially when inserting these identities, these shared identities, gives you more less rigid maps than in a ordinary duoidal category. It is really nice to have this sort of visual aid. So I use this word expressible because we don't actually get all posets this way, or even all finite posets. And so expressible posets are basically just defined to be the ones that arise in this manner. So either they're empty, corresponding to the unit, or they are some combination of joins and disjoint unions of singleton posets. So we call them expressible because there is some expression in terms of tensor and tri that, when applied to singleton posets, gives us the poset that we're working with. And we can actually recognize when a poset is expressible. So we define it just in this inductive manner that sort of clearly corresponds to these expressions in a physical duoidal category. And then we find, okay, what's the simplest example of a poset or a finite poset, which is not expressible? And if you look at this one here, this zigzag, you can see that if you try any combination of any partition rather of the four elements of this poset, you won't be able to see that it's the disjoint union of them or the joint. So it's connected, and any splitting of this into two is not going to be realized as a joint. There's going to be some relations missing. For instance, there's no relation between A and D, so it can't be AC join BD. And in fact, we managed to show that this is the only obstruction. You can't have anything of this shape in your poset, or it's going to prevent you from being expressible. But if you don't, then you're good. So a poset's expressible if and only if it's finite and has no full embeddings at Z. So there's no four elements where these are all the relations between them. If you have all of these, then you need to have some extra relations in addition to make it decomposable into joins. And so especially now that we have this sort of nicer condition for when a poset is expressible, it means that we can, in better conscience, start using expressible posets to sort of more formally describe these physical Duoidal categories. So the next thing is using the result from 2 slides ago, that the expressions correspond to posets and the maps between them correspond to certain maps between those posets, to give a more formal description of these physical Duoidal categories. And we're going to do that using a categorical symmetric operad. So this is just like an ordinary symmetric operad, except each level, written x per n, is a category. And in particular, it's the category of these expressible posets with a fixed number of elements n, and these bijective monotone functions between them. And you can see sort of visually how units and composition in this operad work. The unit's the singleton, and composition is sort of substituting. We have a poset, and we sort of draw it as this diagram with single variables, or express it in terms of tensors and tries. And then we have, however, a number of posets corresponding to the number of variables, so in this case 4. And we plug them in. We put them in this picture that I've drawn before. Each arrow here indicates relations between all of the elements in each of these posets. And just as well, this is given by applying these tensors and this trie to these 4 posets in the appropriate order. And this gives a categorical operad. In fact, you can do it for all finite posets. It's epsilon more complicated to describe because we can't use these disjoint union and join operations, but it works very similarly. And because we know that the operations in a physical Duoidal category correspond to these finite posets, and the maps between the structure maps between those correspond to these maps in our categories x per n, that ultimately amounts to saying that an algebra for this operad, where we have this sort of n-area operation for each finite poset and appropriate maps between them, that the algebras for that operad correspond to the physical Duoidal categories. And you can make this statement more or less precise and specific by varying sort of how strict we take it. But so for instance, like strict algebras for this operad, I believe will correspond to physical Duoidal categories where both of the monoidal structures are strict. But we've made some minor edits to that, so I will avoid getting into the very specifics of that. And so before I finish, I just want to do quickly another example that hints at some of the applications that came up while we were doing this project. So there's a very simple physical Duoidal category where the objects are non-negative real numbers, and the morphisms are just the less than or equal to relations. So we take this poset of non-negative reals, we give it 2 monoidal structures, max and plus, which both share 0 as a unit. And to check the interchange map, we see that the maximum of 2 sums will always be less than or equal to the sum of 2 maxima of corresponding numbers. And again, all of these are non-negative, which is relevant to this. And what I like about this example is that it connects up with the runtimes of programs. So if you have 2 programs, with each of which takes a certain amount of time to run, and you run them parallel to each other, then the runtime, if you're doing this efficiently, then the runtime of the 2 of them together will be the maximum. They're running at the same time, so it's just whichever one takes longer. That's how long the whole thing takes. But if you run them in series, one after the other, then you've got to add up the runtimes. And so we get much more into this in the paper than I'll have time to describe here. But if you have like a finite set of programs and some dependencies between them, describing like when, which of these programs need to finish before certain other ones can run. Maybe, program B relies on some computation done in program A, then you can use these more general operations in the physical duoidal category to compute what an efficient runtime for these programs will be, that makes sure that the ones that need to be in series are in series and the ones that can be in parallel are in parallel. And in fact, we can do this for any poset. And in the paper, we get into how algebras for the categorical operad of all finite posets rather than just the expressible ones lets you analyze this in more detail, including situations where you start keeping track of the variables. And so this is just a hint of both some of the applications we did in the paper and some that there's a lot more work to do. And in particular, we sort of got the idea for thinking about these things in this context from conversations we had with Harrison Groden when he was at Topos. So thank you so much. Here is the reference to the paper on arXiv. And thanks so much for coming.
Let's all thank our speaker. So I have a question. Could you go to slide 4 again? Yeah. So do you know about linear logic?
Very rudimentary, enough to anticipate the question, I think. But yeah.
So linear logic also has two tensor products, but the maps relating the two are different than in a duoidal category, unless you equate the two units. Because this second map on your slide here is exactly what's called a linear distribution, which is the basis of the tensor power fragment of linear logic. And one of the nice things about that fragment, and here you would be doing linear logic plus what's called the mix rule, which equates the two units, is that there is a proof theoretic way of generating all of the morphisms in the free one. And there's a proof theoretic criterion to determine whether there is a map between two expressions built up from atoms. That might be worth taking a look at.
Yeah, thank you. That would. I knew as much as to think that if we had some extra condition, that if we had some extra conditions like try being symmetric, I think we get a linear distributive category.
Oh yeah, I was assuming symmetry.
We also there's an example in the paper where there's this extension of linear logic to, I believe it's called BV logic.
Oh, cool.
Where it
BV,
adds.
yeah.
Okay, yeah, good. I'm never sure how familiar things are. So it adds this non-symmetric operation kind of in between the two. Right. And if you have a BV category analogous to that, then the tensor and the trie is the non-symmetric new operation. So yeah, we're aware of the connections there, though I hadn't heard of the proof theoretic thing you're describing. So I'll certainly be interested to look that up.
I'll send you some notes.
Yeah, thank you.
Other questions?
Hi. Yeah, maybe like a sort of naive question coming from like sort of you mentioned connections to sort of processes and parallelism, and maybe more of like from a computer science angle. Is there any sort of semantics of parallel or concurrent processes that you're aware of that might have an implementation in like a sort of physical duoidal category, like pi calculus or CCS or something like that?
So I don't know the answer to that, but it's definitely something I'd be interested in, and that I've spoken a little bit with Harrison about, because I know he's part of a group doing some really cool looking analysis of program runtimes using type theory, and we get more into it in the paper. So I tried to sort of construct at least based on what I currently know, sort of the nicest picture of this, and you can build this you can build this category whose objects are basically like contexts where you've got some types and elements, and morphisms are programs between them generated by some atomic programs, and you can sort of mark each of those programs with, I mean, you got to kind of assume they're all constant time, which is why this is very sort of initial.
Sure.
All right, but you can mark them with elements of this physical Duoidal category using the extra structure it has. So
awesome. Yeah. Thanks.
So we have questions from Bob and then Anna.
Bob, you're muted.
We still can't hear you, Bob. No. Why don't you type your question in the chat? And in the meantime, we'll hear Anna's question.
Are you hearing me?
Yeah, we hear you.
Oh, great. So thank you, Brandon, for the talk. I was thinking, did you try to do something with quantals? Like, so you're considering here non-negative real numbers. And if you put the infinity in this, then you will obtain something that we call a quantal. So we have that the multiplication will distribute over the supremum. So I was just thinking if you think about this, and if something special happens in this case or not.
Yeah, it's not something I've thought about, but it sounds like something maybe I should.
I think that it would be nice because it's related with my research, but thank you for the talk.
Oh yeah, cool. Well, yeah, I'll look into that. Thanks.